Now let's talk about implementations. Well, certainly there are a lot of different ways of implementing binomial queues, and you may define your own methods of implementing a binomial queue. But one method introduced in our textbook is this. The binomial queue is implemented by an array of binomial trees. Means an array of tree pointers. Okay, at each position, the pointer pointing to the root of the corresponding binomial tree. So this is the basic structure. It's an array of binomial trees. But there are still other details to be considered. Let's take a look at this table. Here, I will list some important operations like delete min. And so the property of the structure we must have for delete min is that we must be able to find all the subtrees quickly. When we delete the root of b sub k, we must be able to create a new heap in log n time. That is, each child must be visited once to guarantee that delete min can be done in log n time, right? So we must be able to find all the subtrees quickly. And the next one is in merge. Remember that I also mentioned that in order to make sure that the merge can be done in log n time, we must guarantee that the children are ordered by their sizes or by the heights. Okay, so these are the properties we must have when we design the data structure to implement a binomial queue. So here comes your first discussion question. How can we implement the trees so that all the subtrees can be accessed quickly? All right, now time to pause the video and think about it. All right, so what's your solution? Notice that each tree in a binomial queue is no longer a binary tree, it's an ordinary tree. To represent an ordinary tree, in the fundamental course, we have studied one method, right? Do you still remember? That is the left child next sibling structure, right? It means that each node contains two pointers. The first one points to its first child. It's called the left child, right? And the next pointer is pointing to its sibling. And therefore, all the siblings, or say all the children, are chained in one linked list. And therefore, once their parent is removed, we can follow the left child link of its parent to reach the head of that linked list, and then visit those siblings one by one. Okay, so that is the solution for delete min. Right, the next question is about merge. In which order must we link the subtrees? Increasing order or decreasing order? Now pause the video and think about it. So which order would you prefer? Increasing or decreasing? Well, the answer is, since the new tree will be the largest one, and therefore we should maintain the subtrees in decreasing sizes. What does it mean? Well, think about this. Say, if we have one root plus several subtrees, and if the subtrees are linked in increasing order, what's going to happen? Increasing order means the first child will be the smallest tree, and the next one is larger. It gets larger and larger. That's in increasing of their sizes. If they are linked in this way, and then when we're supposed to merge two trees of the same size, what must we do? Because the new coming tree has the same size as this whole tree, and therefore it must be the tree with the largest size. And if all the children are linked in increasing order of their sizes, this new tree is supposed to be the last one. And therefore, we start from the root and follow its left child link and then we have to scan the whole linked list to find the last position and attach the new tree to be the last child. And it's going to take time, right? But if we maintain the subtrees in decreasing sizes, means what? Means the largest tree is supposed to be the first tree. Then when we merge two trees of the same size, the new coming tree is the largest one, and it's like inserting a new node as the first node in the linked list. It takes only a constant time. Okay, so that's the reason. Okay, so for example, given a binomial queue like this, it's going to be implemented in this way. First of all, we're going to have an array of pointers. Each pointer points to the root of the corresponding tree. So at position 0, it points to the root of b sub 0. And since we don't have b sub 1, this pointer will be a null pointer. So at position 2, there's supposed to be a pointer pointing to 14, to this node. Okay, and at position 3, there's going to be another pointer pointing to the root 12. Follow the left child link of any node, we can find its largest subtree. Okay, and all the subtrees are linked in decreasing order of their sizes. That is how a binomial queue looks like in a program. Okay, so this is basically the tree node structure. We have a normal element field plus left child and next sibling, 2 pointers. Okay, so the binomial queue is a collection of the trees. It's an array of tree pointers, where bin tree is a tree pointer. And here we also declare an integer to record the current size, that is the total number of nodes in this binomial queue. And then let's check out the implementation of some of the important functions. The first one, the simple one, combine trees. That is to merge two equal sized trees into one. It's quite simple and straightforward. The first step is merely to make sure that when we really do merging, make sure that T1 is the one that contains the smaller root. Okay, if T2 is smaller than T1, then we should swap the positions of T1 and T2. Okay, so while we are here, so starting from this line, is guaranteed that T1 contains the smaller key, and therefore it will be returned as the root of the resulting tree. So basically what we're doing here is this. So we have two trees. Make sure that T1 contains the smaller key. Okay, now let T2 next sibling points to T1 left child. And then what? Change T1 left child to be pointing to T2. And return T1. That's it. What is the time complexity? It takes only 2 steps basically, so it's a constant, right? So it's very simple to merge 2 trees of equal size. Now here comes the real challenge, the merge function. I would suggest you to pause the video to read this piece of code by yourselves first. Okay, I guess you're gonna take 5 to 10 minutes. And when you come back, we'll go through this line by line together. Okay, so let's check it out. The first line is about error checking. So every priority queue would have a limit of capacity. If the capacity is not large enough to hold both heaps, then we return an error message. Okay, and then here we are updating the current size of the resulting heap. Okay, since we are supposed to return heap 1, we're supposed to return heap 1. So the current size of heap 1 will be updated to be the total sum of the two sizes. Okay, and what's interesting is in this for loop, obviously I starts from 0 to somewhere. I gives the index of the current tree. So I goes from 0 and is incremented by 1 step by step, means we're checking those trees one by one. So I should goes from 0 to what? To log n, right? So one way to implement it is that we take a logarithm of the current size of h1 and record that number. So that I goes from 0, I++, until I is greater than that log n. That's certainly one way to implement it. But let's see, what is going on here? Well, I is incrementing, we set up another variable j. Let j starts from 1. 1 is what? 1 is the size of b sub 0. When I points to b sub 0, j is 1. That is the size of b sub 0. When we increment I, we will double the size of j. Which means, for example, when I equals 1, j will be 2, where j still gives the size of b sub 1. Right? So basically, I is the index of the trees, and j gives the corresponding size of the trees. So instead of taking logarithm of the size, we just check the size j. Okay, well, j is no larger than the current size, we can keep going. But my question is, why is this the correct stop condition? Think about it, alright? I'm not gonna explain it here. Take it as part of your homework to figure it out. It's not so complicated, but it's also not so straightforward. Anyway, in this for loop, we're supposed to merge the trees one by one. As T1 points to the corresponding tree in H1 and T2 for H2. Okay, what is this? Did you get it? This is actually a very smart implementation. So what is this? Think about T1. T1 is a pointer, right? If T1 is a null pointer, what's going to happen to this? By doing not T1, we're supposed to get, if T1 is a null pointer, we're supposed to get 1, right? And not, again, we're supposed to get 0. So if T1 is a null pointer, we can obtain the number 0 here. And if T1 is not a null pointer, what do we get? We get not T1, we get 0, and not 0, we get 1, right? So it's a very smart implementation to turn the status of a pointer into a number, 0 or 1. Okay, but what is happening here? It's like we're assigning each digit to a tree. So it takes 3 bits to store the status of the 3 trees. Multiply this one by 2 is a bit shift to the left, right? No matter what T2 is, whether it's a null pointer or not, we get either it's 0 or 1. Multiply that number by 2 means we shift it to the left by 1 bit, right? So multiplied by 4 is actually shifting this number to the left by 2 bits. And therefore, these 3 bits correspond to the status of these 3 trees. And after this calculation, we're supposed to obtain a number. So for example, if that number is, say, 5, we're here. Okay, in case that this number is 5, that means the binary form of 5 is 1, 0, 1. It means what? It means we do have T1, but we don't have T2. At meantime, we have another tree that is carried over from the previous step. And therefore we have 1 plus 1. 1 plus 1 gives 0 plus another tree carried over to the next step, right? So here's what we do. We're going to combine the trees of T1 with carry, T1 plus carry, and assign the resulting tree to carry, and carried it over to the next step, okay? And set this tree to be null, because 1 plus 1 was supposed to get 0 at this position, right? And then let's look at the most complicated case, 7. Okay, if this number is 7, means the binary number is 1, 1, and 1. What do we get? It means that we are supposed to merge T1 and T2 and carry it over to the next digit. And at the meantime, keep carry at the current position. So keep carry at the current position and merge T1 and T2 and then carry this tree to the next step. And afterwards, we like to clean up H2, so set H2 to be null. Now I hope you can understand the whole picture. And this is about merge. Next is delete min. Okay, again, I would suggest you to pause the video and check out this piece of pseudocode by yourselves first. And then when you come back, we're gonna check this one out. Alright, so skip those error checking steps. The delete min really starts from this line, right? So step 1 is, before we delete min, we must find min. Okay, so this is for finding the minimum item. It's very simple. Right? For each I, for each position, we just check the trees. If this tree is non-empty, and we check the element. Okay, if this element is smaller, we update the min item and record this position to be the position of the minimum tree. So after this step, the minimum key is stored in min item, and min tree records the position of that tree. Now let's assign this tree, the root of this tree, to a temporary pointer called deleted tree. Okay, so now deleted tree points to this min tree. And then move on to step 2. We're supposed to remove this tree from the original heap and to obtain another heap. And that's very simple. We just set this link to be null. Then we have remove it from the tree. But this tree is recorded by this deleted tree. Okay, now step 3, we're supposed to remove the root and then assign its children to create a new heap, right? This is how we remove the root. Before we remove the root, okay, let old root points to the deleted tree, and then deleted tree is moved down to its left child. Now deleted tree points to its first child. And then it's safe to free the old root, so we remove the root. And then we're supposed to initialize an empty queue. It's called deleted queue. And the size of this queue is this. What is this? This is 2 to the power of min tree minus 1. Why? Because what is min tree? Min tree is this I. It's not only the position, it also corresponds to the height of the tree, right? At position I, b sub I has the size of 2 to the power of I, right? That's 2 to the power of min tree. That gives the total size of that deleted tree. And now, after the root is removed, we minus 1. So take away 1 root, and this is the remaining current size. Alright, and this part is very simple. We just visit everyone along that next sibling list and assign each root to the corresponding tree. That's all. here we are updating the current size of h. What is that? This h is this one. Okay, so we have deleted one tree from this h, and therefore we are deleting this is the size of that deleted tree. Alright, and finally merge these two heaps. Merge these two heaps. And of course, don't forget to return the min item at the end. And so much for delete min. One detail is that in this pseudocode, we are iterating from 0 to the maximum number of trees, and this can be replaced by the actual number of roots. Again, the question is, what is the actual number of roots? It's log n, right? It's the logarithm of the current size of h. But do we really need to calculate that logarithm? Certainly not. We can just do the same thing as we have done in the merge, right? Set up another variable j and you know what to do.